All right, welcome to another deep dive. This time we're taking a close look at all those physics problems and lecture notes you sent us.
Looks like someone's getting a crash course in electrostatics.
Exactly. Lots of questions about charges, fields, forces, all those fun things. So, to break it down, make it clear, and maybe even have some fun along the way, kind of like your own personal physics tutor.
I like that. Always happy to demystify these concepts.
You've got a bunch of problems dealing with Coulomb's law, so that's a good place to start.
Yeah, Coulomb's law, it's kind of the foundation of electrostatics, right?
Exactly. Concept one, Coulomb's law. It tells us how electric charges push and pull on each other.
Like gravity, but for charges.
Right. Instead of masses attracting, we've got charges either attracting or repelling.
Opposites attract, just
Ah.
like in Killis. Well, no.
Yeah, exactly. So let's take a look at this problem from one of your YouTube videos. Dr. Rao presents two charges, each 2 nanocoulombs, hanging out in a vacuum 3 meters apart.
Classic setup.
He asks, what's the force between them? Now, Coulomb's law gives us the tool to calculate that force, doesn't it?
It does. The force depends on the charges and how far apart they are.
Exactly. Bigger charges, stronger force, greater distance, weaker force. Did you get an answer for this one?
Yeah, I plugged the numbers into the Coulomb's law equation.
Yeah.
No need to be scared of those nanocoulombs. They're just tiny charges.
Absolutely. So what did you end up with for the force?
Let's see, 4 times 10 to the minus 9 newtons, a tiny force for those tiny charges.
Perfect. You've got the Coulomb's law calculation down. Now let's visualize how a charge influences the space around it. That brings us to concept 2, electric fields.
Ah, yes, electric fields. Invisible, but powerful.
Think of it as an aura surrounding any charged object, like a force field.
And this field tells us what force another charge would feel if it were placed in that space.
Right. So in another problem, Dr. Rao presents 2 fixed charges. One's -5 microcoulombs, the other is +10 microcoulombs.
Okay, a negative and a positive charge. Their fields will interact.
He asks, where could the electric field be 0? Think about it. One charge is pushing, the other's pulling.
So there might be a spot where those pushes and pulls perfectly cancel out.
Exactly. A point is 0 net electric field. But where would that be? Consider those charges and their strengths.
Well, it can't be between them, because both fields would be pushing or pulling in the same direction there. And it can't be closer to the stronger positive charge. Its field would dominate. So it has to be on the other side of the weaker negative charge, further from the positive one,
I
right?
got it. It's like a tug of war.
Yeah,
Sometimes the weaker side wins by strategically positioning itself further away.
I like that analogy.
Now, ready to up the challenge a bit.
Always.
This time we've got 3 charges forming an equilateral triangle, plus Q, minus Q, and minus 2Q at the corners. We want to find the resultant force on an electron placed right in the center.
Oh, this is getting interesting. Multiple charges, and they're not all in a line.
Exactly. And we can't just add the forces like simple numbers. We're dealing with vectors here.
Right, vectors. Each force has both a strength and a direction. So we need to consider those directions carefully.
So how do we handle these vectors? Think about breaking them down into components.
Components. Right, we can break each force vector into horizontal and vertical parts. Then, the forces pushing or pulling in opposite directions along the same axis, they'll partially cancel each other out, right?
Exactly, like force vector Tetris.
Then, whatever's left, we add those components to find the final force and its direction.
Now, Dr. Rao emphasizes that the force on that electron isn't just directed straight at the strongest charge, that minus 2Q. Why is that?
Because we have 2 negative charges pulling. Even with the positive charge pushing, the combined pull from those negative charges will create a stronger net force, just in a slightly different direction.
Great point. It's a good reminder that charge interactions can have surprising results. Okay, so far, we've been looking at forces between charges in a vacuum. But what happens when we add different materials to the mix? That brings us to concept 3, permittivity.
Permittivity, it's like how permissive a material is to an electric field.
Exactly. Some materials are better hosts for electric fields than others.
Like some materials let those fields pass through more easily.
Right. Dr. Rao throws in a problem where we have 2 charges, equal charge, initially separated by a distance d in free space. They experience a certain force. Then we bring them closer, separated by a concrete wall with a thickness of d2. The permittivity of concrete is 4 times that of free space.
So concrete, it's denser than free space.
Exactly. How does that change the electric force between the charges?
Well, the charges are farther apart overall because of the wall, so you might think the force decreases. But concrete's permittivity, it's like it can store more electric potential energy, which actually strengthens the electric field.
So the increased distance is completely offset by the concrete's higher permittivity.
Right. The force between the charges remains the same.
Whoa, counterintuitive. It shows how the material between the charges can really change the game. Now let's shift gears and focus solely on distance. We have a point charge, Q, located at point X. Then we have two other points, Y and Z, positioned such that the distance YZ is twice the distance XY. The question is, what's the ratio of the electric field strength at point Y to the electric field strength at point Z?
So it's all about how distance affects the field strength.
Got it. Remember, electric field strength decreases with distance.
Inverse square law. Double the distance, the field strength drops by a factor of 4.
Bingo. Now in this problem, point Z is 3 times farther from the charge Q than point Y.
Okay, so 3 times the distance. That means the field strength at point Z should be 9 times weaker than at point Y.
You nailed it. The ratio is 9.1. Even small changes in distance can have a big impact on that field strength. Ready for another interesting one?
Absolutely. Hit me with it.
All right. This time we've got two very long parallel plates, X and Y, with equal but opposite charges. The potential on plate X is Vx, and on plate Y it's Vy, with Vx being greater than Vy. We have a little positive charge Q, with mass m initially held at rest between the plates. Then we release it. Which plate will this charged particle move towards?
Okay, so we need to think about those potential values.
Exactly. They tell us something important about the charges on the plates.
Higher potential means a higher concentration of positive charge, right?
Exactly. So plate X, with a higher potential, must be the positively charged one.
Right. And since our particle is positive, it will be attracted to the negatively charged plate Y and repelled by plate X.
So it'll zip towards plate Y.
Exactly. That difference in potential creates an electric field that guides our little charge.
The problem also asks for the kinetic energy the particle will have when it reaches plate Y. What principle should we use here?
We need to think about work and energy. The electric field is doing work on the particle as it moves. That work is equal to the change in the particle's potential energy.
And that change in potential energy is directly related to
the kinetic energy the particle gains. It's a classic energy conversion. Potential energy stored in the field is transformed into the kinetic energy of the moving charge.
Spot on. Okay, let's get a bit more visual. Imagine a vertical wall with a uniform positive charge spread across its surface.
A charged wall. Sounds intriguing.
Concept 5, surface charge density, comes into play here. It tells us how much charge is packed onto a surface.
So a higher surface charge density means a stronger electric field coming from that surface.
Exactly. More charge, more punch. Now, this positively charged wall produces a uniform horizontal electric field perpendicular to the wall. The problem even provides a formula. E equals sigma divided by 2 epsilon. Sigma represents the surface charge density, and epsilon is the permittivity of the medium, which we can assume is air. A small positive charge is suspended in equilibrium from the wall by a thread.
Suspended? Like a tiny pendulum.
You got it. But because of the electric field, the thread makes an angle with the wall. Like that invisible force field is pushing the charge away. The question is, what's the horizontal force acting on the ball?
Okay, so we have a few forces at play here. Gravity is pulling it downwards. And we have the tension in the thread acting along the direction of the thread.
Right. And since it's in equilibrium...
But the horizontal component of that tension force must be equal and opposite to the horizontal force from the electric field.
You got it. And we can figure out that tension force component using some trigonometry, right?
Yeah, the angle the thread makes with the wall allows us to use sine and cosine to find those horizontal and vertical components. Then we can easily determine the horizontal force due to the electric field.
Perfect. Now the problem gives us the charge on the ball and asks us to figure out the surface charge density, sigma, on the wall. How would we do that? Remember that formula? E equals sigma divided by 2 epsilon.
We can use the horizontal force and the ball's charge in the equation F equals QE to get the electric field strength, E. Then plug that E value into the formula with sigma and epsilon and solve for sigma.
Beautifully done. You've connected the force on the ball to the field strength and then linked the field strength to the charge density on the wall.
It all comes together.
Okay, now for a fun twist. Imagine that thread suddenly snaps. What happens to our little charged ball?
Uh-oh. No more tension force. So now it's just gravity pulling it down and the electric force pushing it horizontally away from the wall.
So what kind of motion will we see?
A combination of those two forces. It'll move both downwards and away from the wall. Since the forces are constant, it'll follow a parabolic trajectory, just like a projectile.
It's like a physics dance, with gravity and the electric field choreographing the moves.
I love that.
Okay, let's pause here for now. We've covered a lot, from forces between charges to how electric fields can influence a charge's motion.
Welcome back. Ready for round 2 with electrostatics.
Absolutely. We've got those basics down, so let's push a little further. In the last part, we touched on electric potential. Yeah. You sent over a problem that really digs into that concept.
Oh yeah, this one's a bit of a brain teaser.
Concept 6, zero electric potential. That sounds kind of strange, right? Dr. Rao asks, can the electric field be zero at a point where the electric potential is not zero? What do you think?
It makes you think about the difference between electric field and electric potential. Like, the field is all about the force a charge would feel at that point.
Right, like if you put a little test charge there, would it feel a push or a pull?
Yeah, exactly. But electric potential,
Yeah.
it's more about the energy.
The energy it takes to bring a charge to that point.
Right. It's like, imagine you're on a mountain standing on a flat plateau.
Okay, so no slope, no immediate force pulling you down.
Exactly. But you still have potential energy because you're high up.
Ah, so even though the electric field might be zero, the potential might not be.
Makes sense.
Dr. Rao gives this example with a positive point charge sitting above a metal plate that's at zero electric potential. Then he asks, which diagram correctly shows the electric field lines between the charge and the plate? Think about how conductors behave in electric fields.
Oh, conductors.
Yeah.
Those are the materials where charges can move around freely. So the metal plate, it's going to mess with the field lines from that positive charge, right?
Definitely. Those lines can't just go straight from the charge to the plate.
Nope. They have to follow some rules, especially around conductors.
Right. What's that rule about how those field lines meet the conductor?
They have to hit the surface at a right angle, perpendicular, like a perfect T.
Perfect. So picture those lines starting at the charge and then curving to meet the plate at 90 degrees.
Like the metal plate is trying to shield itself from the field, bending those lines out of the way.
Great visual. Now let's try a problem where we're actually moving charges and looking at how the potential energy changes.
Yep.
We have two charges, A plus Q and a minus Q, separated by a distance r. We want to find the work required to increase their separation to 2r.
Okay, so we're changing the distance between charges, and work is related to potential energy, right?
You got it. Now, think about those charges, plus and minus. What kind of force is between them?
They're opposites, so they attract each other.
Right. It's like trying to pull apart two magnets that are stuck together.
You have to put in effort, you have to do work to move them further apart.
Exactly. You're fighting against that natural attraction. So what does that tell us about the work done? Is it positive or negative?
You're putting energy into the system, so the work must be positive.
Perfect. Okay, let's switch to something a bit more visual again. We have a diagram showing equipotential surfaces for a bunch of charges, and we want to draw the electric field lines for this whole setup.
Ooh, a little electric field art.
Exactly. What's the key relationship between those equipotential surfaces and the electric field lines?
They always cross each other at right angles.
Right. The field lines cut right through those equipotential surfaces, like imagine contour lines on a map, and the field lines are rivers flowing downhill.
Always perpendicular, like the water follows the steepest path.
Great analogy. What else can we tell about the field lines just by looking at those equipotential surfaces? Think about their spacing.
Ah, the spacing. That tells us about the field strength. Closer spacing means a stronger field, right?
Right. It's like contour lines on a map, too.
Yeah.
The closer together they are, the steeper the terrain. So when you're drawing those field lines, make sure you adjust their spacing to show those variations in field strength.
Got it.
All right, let's shift back to motion and see what happens when a negatively charged particle enters a uniform electric field. This time, the particle's initial velocity is perpendicular to the field lines.
Perpendicular. So it's moving sideways compared to the field.
Exactly. What do you think will happen to its path? Does it remind you of anything we've talked about before?
It's like, remember that projectile motion example?
Ah, you're on the right track.
Instead of gravity pulling it down, now we have the electric field pushing it sideways. So a parabolic path.
Bingo. That sideways force from the field curves the particle's path. Now, what if that charged particle starts at rest in the uniform field? No initial velocity this time.
So it's just sitting there, and then the field turns on.
Exactly.
Well, since the field exerts a constant force, it will start accelerating. in a straight line, either with or against the field, depending on its charge.
Perfect. It's like free fall, but the electric field is playing the role of gravity.
Okay.
Okay, ready for one last conceptual challenge to really test your understanding?
Get me with it.
All right. Let's say we've got a charge placed at a point where the electric field strength is 0. Does that automatically mean that the electric potential at that point is also 0? What do you think?
0 electric field. So no net force on a charge placed there. But does that mean the potential access to be 0? Not necessarily, right?
You got it. Explain why.
Because the electric field being 0 just means that all the forces from different charges are perfectly canceling out at that point. But the potential is about more than just the field at that one spot. It's determined by all the charges in the system.
Excellent point. So even though the forces are balanced, the potential might not be 0.
Exactly. Like imagine you're balancing precariously on a tightrope.
Okay, so the forces are balanced. You're not falling.
Right. But you still have a lot of potential energy because you're high up.
Perfect analogy.
Okay.
You've really got a handle on the difference between field and potential.
All right, welcome back. It's time for the grand finale of our electrostatics deep dive.
I'm ready to wrap up with some more electrifying challenges.
Let's start with one that combines a few concepts: electric fields, potential difference, and even projectile motion.
Okay, I like where this is going.
So picture this. We have a small positive charge, and it's initially placed at a point with an electric potential of 100 volts.
All right, so it's in a region with some electric potential energy already.
Exactly. Then we release it, and it accelerates through a potential difference of 50 volts.
So it's like it's rolling down an electric potential hill, picking up speed as it goes.
Exactly. It gains kinetic energy as it moves through that potential difference. And then it enters a region where there's a uniform electric field pointing downwards. What happens next?
A uniform field.
Mm-hmm.
That means a constant force on the charge.
Yeah,
And it's downwards. So it's kind of like we're throwing a ball horizontally off a cliff.
you got it. With gravity pulling it down, that ball follows a curved path, right?
Yeah, a parabola.
Same thing here, but instead of gravity, it's the electric field doing the pulling. Our little charge will follow a parabolic path too.
I love how those different physics concepts all come together. Okay, let's try one that focuses on the work required to move charges around. We've got 2 charges, plus Q and Q, separated by a distance r. And we want to know the work required to increase their separation to 2r.
Okay, increasing the distance sounds like we're putting in some effort.
Right. Think about those charges, plus and minus. How do they feel about each other?
Opposites attract, so they want to be close together.
Exactly. And we're trying to pull them further apart, like separating 2 magnets that are stuck together.
We're going to have to work against that attraction.
And how does this relate to the electric potential energy of the system?
The work we do goes into increasing the potential energy.
So positive work.
Positive work. We're adding energy to the system.
Okay, I see that. Now let's get visual again. Remember those equipotential surfaces?
Yeah, like contour lines on a map.
Imagine we have a diagram showing those surfaces for a bunch of charges. Your mission, should you choose to accept it, is to draw the electric field lines for this whole configuration. What rules do we need to keep in mind?
Okay, first rule. Field lines always cross those equipotential surfaces at 90 degrees. Perpendicular, like a perfect T.
Right. The field lines cut straight through those potential lines.
And the spacing of those potential lines. That tells us something important about the field, too. Closer spacing means a stronger field, right?
Absolutely. It's like those contour lines on a map again. Close together, steep terrain. Far apart, gentler slopes. Make sure your field lines capture those variations in strength.
I'll get my virtual drawing tools ready.
Now let's analyze the motion of a charged particle in a uniform electric field. Imagine a negatively charged particle entering the field. Its initial velocity is perpendicular to the field direction.
Perpendicular, so it's coming in sideways.
What do you predict for its path?
It's going to experience a constant force from the field, pushing it sideways, but it also has that initial sideways motion, so the path. It's going to curve, like a parabola.
You're on fire. A parabolic path, just like that projectile motion we discussed earlier.
Physics is so interconnected.
Right. Now let's change things up slightly. What happens if that charged particle starts from rest within the uniform electric field? No initial velocity this time.
So it's just hanging out in the field, minding its own business.
And then, bam, the field is turned on.
Since it's starting from rest, and there's a constant force on it, it'll start accelerating in a straight line, either with or against the field direction, depending on its charge.
Nailed it. Okay, you ready for one last conceptual challenge before we wrap up?
Bring it on. I'm feeling supercharged.
All right, here it is. We have a charge placed at a point where the electric field strength is 0. Does that automatically mean the electric potential at that point must also be 0?
Ooh, a tricky one, I think.
Uh,
Not necessarily.
you're right. Tell me why.
Zero electric field. It just means all the forces from different charges are balancing out at that point, like a perfect tug of war, but potential. It's
Right.
not just about the field at that one spot. It's determined by all the charges in the system.
So even though the forces might be balanced, the potential could be something other than 0.
Exactly. It's like standing at the top of a hill, right on the peak. You're not feeling pulled in any direction, but you still have potential energy because of your height.
That's a great analogy. So we've come to the end of our electrifying journey.
We've tackled some tough problems and really gotten a feel for the power of electrostatics.
It's amazing how these concepts underpin so much of our world, from tiny atoms to the circuits that power